Hi everyone, my name is Sofiane Guessasma. I'm a research scientist working at the BIA in Rhineland. First of all, I would like to thank the organizers for giving me the opportunity to deliver this talk, which tackles one of the aspects from Iman's thesis. I'm also sorry for not being able to attend the conference today. I leave my email address in case you have comments or questions, and I'm pretty sure that one of my colleagues, Magdalena Orgi, can also answer questions. They took part in the thesis supervision. So the talk today is about modeling of mechanical behavior or P snacks. Before going any further, let me give you some elements of the context of the study. So the idea is to find different sourcing of the protein from plants, which offer different aspects like the lower CO2 emission, less used agricultural land, and high protein content. The subject of Iman's thesis focused more on pea protein, and the idea was to find out more about the effect of this protein on the extruded food texture. So speaking about the extruded food texture, this brings out the effect of the area structure, which also depends on the cell wall properties. In the case of the P composite material, the idea was to better understand the link between the microstructure of the cell wall on the mechanical behavior at the solid phase, which also will affect the properties of the foam structure as well. So the idea was to design some P-based starch protein composites using twin screw extrusions, using different formulations and different specific mechanical energies. We did also some morphology and macroscopic behavior determination using CLSM and 3D bending testing, and also some local mechanical property behavior determination using nano-indentation test, and combine all these experimental data towards predicting the behavior of the P protein composite material using finite element computation, both at the macroscopic and the microscopic scale. Today I'm going more to talk about how the finite element computations was used to determine the macroscopic behavior, but we will a bit talk about the determination or the determination of the local properties using nano-indentation at the end of the presentation. So these are the samples that were used in the study. These range from the protein flour to starch pea protein composites with different pea protein contents ranging from 30% up to 60%. So this is a typical engineering stress engineering strain response for a 3P or 3-point bending test under a water content of 12%. As you can see here, we move from a ductile behavior for the starch material to something that is more elastic plastic behavior for the composite materials, down to a brittle behavior for the flour and the protein material. So to comment on this curve, we could see clearly that there is a large contrast in mechanical behaviors, which can be explained by the transformation of the constituents and the blends, and also due to the various formulations that were obtained from the extrusion process. At the same time, we could see clearly that the protein blending with the starch is responsible for the lower ranking of the mechanical response of the composites due to the brittleness of the protein aggregates. In order to explain these correlations, we used SESM imaging, where you see here the starch phase appears in gray level and the protein in green color. So basically, we see the effect of the starch depolymerization as a main aspect of the matrix transformation, but also the appearance of the protein aggregates, which are more or less dependent on the extrusion process. So there's different morphologies that are obtained by only tuning the SEME and the formulation. In order to further quantify the effect of the process parameters on the morphology of the protein aggregates, we use an index called the interface index. This index is just the ratio between the total aggregates parameter over the total aggregate area to the square root. So we related this index to the macroscopic mechanical behavior of the P composite. So here's the flexural models, for instance, as a function of the interface index, where we see a more or less nonlinear behavior where the flexural modulus increases with the increase of the interface index. So there's also some more or less dispersion in the global mechanical behaviors at the same interface index, which can be related to the variability of the intrinsic properties of the phases, but also to the degree of transformation at SME level. So in order to further quantify the effect of the protein on the flexural behavior, we use the finite element computation at the macroscopic scale. So this is a kind of sketch of the scheme of the FE simulation. We use an isotropic elastic model for which you need only Young's modulus and Poisson coefficients for the phases, but also in order to account for the plasticity of the composites, we use the Voss law, which is only determined by three main parameters: the yield stress, the saturation stress, and the saturation exponent. So the behavior of this law is sketched on the right part. So this is the parameter window that we use it for simulations for both Young's modulus, but also the three other parameters related to the plasticity behavior. And here is the predicted behavior of all samples, including the composites, the flour, and the starch phase as well, where we could see that we achieve a pretty good agreement between the experimental and the numerical behavior. In order to quantify further these effects, we sketch here the Young's modulus dependence on the interface index, and surprisingly, we see that there is a linear increase of the stiffness with the increase of the interface index, which this appears to be surprising because we would think that the lower properties at the interface would trigger a lower behavior, but in this case we see the opposite behavior. If you look at the tensile strength as a function of the interface index, we see more negative correlations, which could be also explained by the fact that you have a weak link between the two faces. The examination of the SEM fractalography shows clearly the cohesion between the starch and the protein, and the explanations of the two curves can be sketched as follows. So the alteration of the load transfer at the starch-protein interface could be more related to the interfacial resistance than to the interfacial stiffness. So this is the main hypothesis that we used to, and we wanted to verify this from the nano indentation results. And for that, we needed more information to be able to do the micro-mechanical models that Imens tried during his thesis. So the basic idea is how to determine both the phase properties, but also how to determine the interface properties as well. For that, we used the nano indentation experiments at Imperial College, and for all the samples that have been studied previously at the microscopic scale. And the surface finishing was a bit a critical issue to solve because of the sensitivity of the results to the surfacing of the samples. So definitely these are some of the grid of indents that we achieved using a Bekovich-like indenter. And we succeeded in doing a mapping through the entire composite, and it shows that depending on the depth of the penetration of the indenter, you could get a quite varied results. So we used a large depth profiling from 1 up to 7 micrometers, and we achieve a good stability in terms of mechanical properties at a depth of 3 micrometer. One of the things that we verified is that the Young's modulus associated with the protein is lower than the modulus of the starch, as we have seen this from the global tensile testing. But also we see here, if we do some indentation at the interface between the starch and the protein, we see clearly that the hypothesis of a higher stiffness at the interface is verified by and confirm the idea that the alteration of the load transfer is more related to the decrease in the interfacial resistance rather than the stiffness at the interface. So to conclude, we have seen that various P-starch protein composite morphologies can be triggered by using a quite interesting combination between the SME and the protein content. From the macroscopic viewpoint, the 3-point banding test reveals that we could achieve a high variability in terms of behavior, ranging from the brittle to the elastic plastic behavior. We have also seen that the load transfer at the interface in these composite materials trigger more an effect on the interfacial resistance than the interfacial stiffness. And these were confirmed by more local mechanical properties, which allows us to determine the interface Young's modulus. Those results were used in a later study to determine the exact stress distribution at the microstructural level, which Imens did in another study. And these were used as inputs for the finite element micromechanical model that I'm not talking about today. So I thank you very much for your attention. Please feel free to ask your questions and leave a message, and I'm happy to answer them. Thank you very much and enjoy the day. Bye-bye.